All right, so this is going to be our introduction to pumps. The first kind of pump we will talk about is what is called a positive displacement pump. So a positive displacement pump is best diagrammed by something that looks like this. And the basic idea of a positive displacement pump is that I am using the motion of an object to physically displace water. All right. I'm not adding energy. I'm actually physically moving the water by moving a solid boundary. All right. So it's the pumping of water by a solid boundary. So we could call it that. Pumping by moving solid boundary. Typically, we're going to have an inlet. I'll put a valve on that. This is our inlet. And we have an outlet. And there's also a valve here, but I'm going to leave it open. And our pump would be filled with water. So this is sort of the starting point. And then in the next point, this piston moves forward, driving the water that was in this chamber into the outlet through our open valve. All right, then that valve closes and our piston moves backwards, but the inlet valve opens. All right, and because the inlet valve is open, now water is going to be pulled in through our inlet. So as this piston moves this way, we get water out of our outlet. And as this valve is closed and the piston moves this way, we get water in our inlet. And now we are back to this state. All right. And so the basic idea is this this motion of a boundary, all right, in a positive displacement pump. We can essentially say that what this is really a flow rate control. And the amount of flow that a pump like this moves is equal to the volume that it can move in a cycle times the frequency of the cycle. All right. All right. Now, a positive displacement pump, you've probably, the example everybody knows is the human heart, right? A human heart is this kind of pump. All right. But there are a lot of examples of other kinds of pumps that are like this, okay? But this is the basics of a positive displacement pump. Now, the second kind, positive displacement pumps are kind of pumps, like I said, they're flow rate controlled. Now, the second two kinds, they're going to talk about two more kinds of pumps, and those are really what we call dynamic pumps. And a dynamic pump these add energy to a fluid, all right, through rotation of an object. Okay. And we have two types. We have what are called axial and what are called radial, all right, or centrifugal. All right, and we'll do a little bit of math on each one of those. And then you can also have mixed, where you have systems that are a little bit of both, okay? All right, now what's the difference between an axial and a radial pump? Essentially, if an axial pump looks like this, where we have flow going this way, an axial pump has some sort of, usually has a little thing here, some sort of shaft here, and it is usually got somehow, like if there's an elbow here, the shaft is going to extend out of it. This thing spins with some value omega, and there are these blades on the rotor, which I'm going to put in blue, And this whole thing is spinning with omega, and it's driving flow in the axial direction, okay? So it's driving flow using these blades this way, adding energy. A radial pump, the difference is a radial pump, typically we would draw it to look like this, sort of like a B. And in a radial pump, my inlet is actually here, this black circle. And around that black circle, I have fluid coming in. I also have these vanes, and I'll put the vanes in blue, so here. All right, these blades, okay? And again, these blades are being driven to spin at some speed. So I have a flow rate Q here coming in, that's my inlet, and then my outlet is actually perpendicular. All right, so my inlet, oops, I didn't want to do that. My inlet is actually in the Z direction coming out of the page here, where this red dot is. All right, and then my outlet is up. All right, and so I'm using the centrifugal motion of the blades, and here I'm driving flow in the axial direction. So quickly, we're going to talk a little bit more about how an axial pump works. All right, so the basic idea with this axial pump is I have this rotor, all right, and on the rotor, it's spinning with some omega, and coming out of the rotor is this blade, like this, all right, and this blade is at some radius r from the rotor in black, so there's this r to the sort of the middle of the blade, which means it's moving at a velocity u, which is equal to omega, the speed the rotor is moving, times rm. All right. Now we've never done an ideal analysis of this, okay, but we never did linear momentum. But you can show that for such a system, then we can use angular momentum to solve this. Now there's something we need to realize, which is that if I have this blade moving, and here's sort of a picture of the blade in 2D, then it's going to have a velocity this way, which is sort of the inlet velocity, and a velocity that way, which is the outlet velocity. All right, and we could break it down into having a velocity, which we'll call the tangent, and then a velocity which is sort of perpendicular, which we're going to just call this way, A1. Okay, so there's a tangent velocity. There's a tangent velocity and the axial velocity. Now it turns out that if I do a balance of angular momentum, and that means that the sum of the moments on my control volume, which would be an impeller blade, equals d dt. Again, we've never done this, but don't worry about it. Control volume, and since it's moments, r cross v, rho dv, plus the integral over the control surfaces of rho r cross v, v dA, or v dot n, the way we write it, dA, okay? Now you can go through this whole analysis, and what you would end up finding is that the torque supplied by the motor, so over here we have omega and a t, right? Right, if it's in a steady state situation, it just ends up equaling the integral over my control surfaces of rm vt, because that's r cross v, times rho va dA. And this VA rho dA, right, this is going to end up basically being our Q. And so what you can find is that this torque actually is equal to rho Q R mean, so the mean radius of the impeller blades, and then VT2, which is the outlet, minus VT1. All right. Now what's important to realize with this pump is that with any pump, right, Q in must equal Q out. These dynamic pumps don't change the flow speed in them. If they did, we'd lose mass conservation. What they do is add energy, okay? And the amount of torque it is required to run these pumps is defined here, all right, for an axial pump.